Hello dear students, I welcome you to this. This is actually the unit which is contained in your this UG undergraduate courses, and it is somewhere in BTech engineering courses in some semesters. Well, the name of the unit will be now linear differential equations of second and higher order. Okay, and I have mentioned here what we will discuss in this, because this is the first lecture that I want to deliver with you on this topic. The topic is linear differential equations of second and higher order. We'll be dealing with in this topic. One is general linear differential equations of higher order, linear differential equations of second and higher order with constant coefficients, which forms the part of your syllabus, either this undergraduate courses or BTech engineering courses in some semesters, and somewhere it is also mentioned symbolic operators that will also come under this. Next and third is we will be dealing with homogeneous linear differential equations. Okay, you have already done homogeneous linear differential equations, but here we will be dealing with those homogeneous linear differential equations which are reducible to this form, linear differential equations of second order with constant coefficients. These are also known as Cauchy-Euler equations. Cauchy-Euler equations are this. I will tell you when we reach here. I will explain why these is called this Cauchy linear equations, and we will be also dealing here solution of second order Legendre's differential equations which are reducible to linear differential equations with constant coefficients. But you should remember that in your this topic where you have the power series, in power series you have to do the Legendre's differential equations and Bessel's differential equation. There you have to do the Legendre's polynomial, but it is not that one. It is something different. That name is Legendre. It is reducible to the linear differential equation with constant coefficients, and that differential equation which you have to deal with in this power series. We will discuss here. I may share some lectures on that. It is the Bessel's differential equation and Legendre's differential equation. It is solution, power series solution. I will write that equation is this form. It is 1 minus x square d2y by dx square plus minus 2x dy by dx plus n times n plus 1 is equal to 0, where n is not equal to plus minus 1. This is the Legendre's differential equation which you have to deal with in power series. Remember this, power series. And here in power series you find out there this Legendre's polynomials which are Pnx. Some of you might have done Qnx. Pnx is very important, and because it is the in descending powers of x. This and this is different. Here we will be dealing with that those Legendre's differential equations which are reducible to linear differential equations with constant coefficients. This is what I am telling you. I am just giving you the description what we will be sharing with you in this topic, linear differential equations of second order and second and higher order. We will be discussing these things. These forms the part of your syllabus. Well, before defining, we have previously this shared some videos on ordinary differential equation. There we did dy by dx plus py is equal to q, where p and q are functions of x. This is also linear differential equation, but it is a linear differential equation of first order. Okay, we will be dealing with linear differential equation of second and higher order. Okay, there we didn't consider any differential equation which is d2y dx square, so on and so forth. Let us have the definitions. Let us take the definition now. We shall take the first definition of linear differential equation. This definition, number 1. Here I will first define again what we mean by linear differential equation, that we define it in case of dy by dx plus py is equal to Q. When we took the lecture on that, what is called the linear differential equation of first order, there we defined something. It is same definition. I will write here a linear differential equation is that in which the dependent variable and its derivative occur in first degree and are not multiplied together. This is actually the fundamental definition of linear differential equation. We have not touched here the order yet. We say what we mean by the linear differential equation is that in which the dependent variable I write here and its derivative is of the first degree. I have already told you that whenever you take the differential equations, courses of study in differential equations, it is a very vast subject. I mean, now this differential equation is first you have ordinary differential equation, then you have partial differential equations. In partial differential equations, you have to do many things like the solution of heat equation, wave equation, and so on and so forth. You must have the language of now differential equation. Language, as I have already told you, the language of the differential equation is actually integration. You must have the master of integration, and then you must have, when you deal with the different forms of differential equations, you must know what we mean by order and degree. You just practice on this order and degree of the differentiation so that you will not have any difficulty for recognizing, I mean, how to recognize a differential equation, how to recognize the character of a differential equation, how we know the which differential equation is one, which is that, which is so on. So you must revise. For that you have we have already shared with you some these lectures on the ordinary differential equation, and if you go the playlist there in our YouTube channel, there is the playlist. That playlist gives you the first lectures on the differential equation, and that second this lecture you will get what we mean by order, what we mean by degree, so on and so forth. So we talk of here it should be first dependent variable and its derivative must occur in first degree. You see, if you have the derivative involving in the differential equation, say dy by dx, and this y is your, this y is your dependent variable. This is your, remember this is your dependent variable. Okay, you say in the definition that y should occur first degree. That means it should have y and dy by dx. And dy by dx in the first, it is, what is it is degree? It is power. Dy by dx power, whole power, that should be always 1. It can be d2 by dx square, d4, that is the order. And we say that these are not multiplied together. If they are getting multiplied together, then it ceases to be the linear differential equation as per the definition. So they should not get multiplied each other. There should not be any term involving x y dy by dx or y square dy by dx. No. If it has some coefficients, we will just deal with this. If it has some coefficients, variable coefficients, those should be the only functions of x, not functions of y. If it has this derivative has the coefficients functions of y, then it ceases to be linear differential equation. Remember this. That was why we say that a dependent variable means y and its derivative occur in the first degree. It should occur in the first degree. First degree means it is highest power should be 1. Even if it is d2y dx square, d4y dx cube, that means order, and y power is 1. Okay, and should not and are not multiplied together. These are not. This is the fundamental definition of this linear differential equation. Now let us come to the fundamental definition of this. We shall now take this one that we have mentioned in our first this, what we mean by general linear differential equation. So accordingly we say a differential equation of the form it is d and y dxn. N is here nth order derivative, d and y dxn plus, let us write here constant, this coefficient p1, n minus 1 derivative dn minus 1 y dx n minus 1. Then I write p2 d n minus 2 derivative y by d x minus 2 plus so on to p of n minus 1 dy by dx plus p and y is equal to 0. This is the differential equation where we have here, where I will take here x because I am defining the general one. Let me take this is equal to x, not yet 0. This is equal to x. Name this equation number 1. Okay, is equal to x I took, where p1, p2, pn and x are functions of x alone, is called, this differential equation is called that general, it is a general linear differential equation of nth order, because the highest order derivative involved is here n. It is the linear differential equation of nth order, and we have mentioned here the coefficient of these p1, p2, pn, x. These are the functions of x alone, is called, this is also a function of x. Now in case this p1, p2 so on to pn minus 1 pn are constants, then we come to this thing, the linear differential equation with this constant coefficients. We have to actually deal with that. I have already told you that we are here in this field that we want to reduce some differential equations with variable coefficients, Legender's differential equation with variable coefficients, which are reducible to the linear differential equations with constant coefficients. Not always we can reduce some forms, some kinds of differential equations, we can reduce them differential equations with the constant coefficients, and then we apply the general method that we will discuss in future. Okay, so this is the linear differential equations, not with constant coefficients. These we took as variables here. Now we come to linear differential equation with constant coefficients. This is first lecture I am giving on definition. Please have a stress on this lecture to know the definition, what we are giving the name to different things. Then it will be very easy for you to solve the these kinds of questions, because BTech students only get the questions there, they don't get the terms, they don't get the definitions. They have maximum number of applications, but the students who are pursuing this integrated 5-year integrated course in mathematics, honors courses in mathematics, BSc course in mathematics, they have to this stress also on terms. They get terms as well as questions there. Okay, now I will define next the this one. It is linear differential equation with constant coefficients. In this case we write a differential equation equation of the form it is a net derivative here dny dxn. Let us write here now a1 dn minus 1 y dxn minus 1. You are observing that here y is of first degree everywhere. Wherever you get y, first degree, not multiplied with any derivative. Okay, a1 plus a2 dn minus 2y dxn minus 2 plus a n minus 1 dy by dx, this is plus a n y is equal to x. Okay, where a1 a2 an are constants. These are constants. Remember that these are constants, and capital X on right side is some function of x only. This is called this equation is called linear differential equation of nth order. We defined here of nth order with constant coefficients. It is with constant coefficients because coefficients are here. It is called the linear differential equation of nth order with constant coefficients. Now if you replace this n by 2 here, this will be the linear differential equation of order second order linear differential equation with constant coefficients. This is the definition. When you have this coefficient is here constant, it becomes the linear differential equation with constant coefficients. Now we shall discuss with you the very important theorem that will tell us how we write the solution of these equations. This is a very important theorem. You should just probe and look into this theorem with the interest what we are doing here. Very easy theorem. This is the theorem that I want to share with you. This theorem states if y is equal to y1, y is equal to y2, so on, y is equal to yn, or n independent particular solutions of linear differential equation, it is this dny dxn plus p1 I will write dn minus 1y dx raised power n minus 1 plus p2 dn minus 2y dxn minus 2 so on p dy by dx, it is pn minus 1 dy by dx plus pny is equal to 0 I will take if these are the n independent particular solutions of this differential equation of this, then y is equal to c1 y1 c2 y2 plus cn yn is complete solution of first. This is a complete solution. Why it is complete? Because we have a fundamental theorem that states the number of arbitrarily constants that gets involved in the solution of the differential equation depends upon its order. If the order of the linear differential equation is second order linear differential equation with constant coefficients, it must involve two constants, C1, C2. If order is third, then three constants. Order is here n. These are the particular solutions, independent solutions, separated, and we combine them with the constants C1, Y1, C2, so on to Cn, Yn. This is also solution. Where you have, where I have mentioned here, where P1, P2, Pn are constants in number 1. I have not mentioned, I should mention it here. Okay, I have mentioned here. This P1, P2, Pn, these are the constants. So this is the linear differential equation with constant coefficients with right side 0. Okay. Then we say this is also the solution. Here C1, C2, Cn gets involved. What is this? And C1, C2, Cn are n arbitrarily constants. और ये n arbitrarily constant जो आप यहाँ पे लिख रहे हैं, these are also linearly independent. They are not dependent, because once they become dependent, two constants can be reduced into single one. It should involve n constants. That is why we say that they are linearly independent. Solutions are also linearly independent. This is the theorem. Very simple proof it has. Let us have the proof of this theorem so that you will come to know how we solve these. Now we have the proof. This is the proof of this result. In the proof, we consider again given linear differential equation of order n with constant coefficients. And what was that? It was dny dxn plus p1 d n minus 1 y dxn minus 1 plus p2 d n minus 2 means n minus 2 derivative dxn minus 2 so on p of n minus 1 dy by dx plus p and y is equal to 0. Where I have mentioned it in the statement that this p1, p2, pn minus 1, pn are constants. We are dealing with when the linear differential equation of nth order has the constant coefficients. Right hand side we take 0 here. How we write down their solutions? If it is known that y1, y2, so on to yn, n solutions are given, we can connect these n solutions by the linearly independent constants. Now it is given, since y is equal to y1, y is equal to y2, y is equal to yn are solutions of equation number 1, given equation number, and they are the solutions, they will satisfy it. This means you have d nth derivative, y will be replaced by y1 dxn plus p1. Solutions means it will satisfy it. Okay, it is d n minus 1 y1 d of x n minus 1 plus p2 d of n minus 2 y1, it is d of x minus 2 so on p of n minus 1 dy1 dx plus pn y1 is equal to 0. Name this second. When y2 is a solution, that will also satisfy. This will imply that dn y2 dxn plus p1 d of n minus 1 y2 here, it is d x n raised power n minus 2 n minus 1, sorry, then plus p2 d of n minus 2 y2 here dx n minus 2 plus so on to plus p n minus 1 dy2 dx plus p n y2 is equal to 0. Let this be third one. Now proceeding this way, I will not write now each and every solution. I will proceed onwards. So when I take y is equal to yn into solution, what will be this? It is dn yn by dxn, that is nth derivative of yn, plus p1 dn minus 1 yn dxn minus 1, p2 it is dn minus 2 yn dx n minus 2 dash so on to p of n minus 1 dyn by dx plus p n yn is equal to 0. Let us name this equation number 4th. Let it be equation number 4th. Now we will prove that this equation number 1 has also the solution y is equal to c1 y1 plus c2 y2 so on to c and yn. For that we will use the value of y here, replace this y by c1 y1 c2 plus c2 y2 so on to c and yn, and solve this equation. And using these values, if we get if that get satisfied, if y is equal to c1 y1 plus c2 y2 plus so on to c and yn satisfies this equation first, that means that is also the solution of this, and that will be called what? The complete solution of this linear differential equation. And finally we will write the observation on that, what this theorem states and where we use it. Okay, let us now see how we prove it. Now let us take, now using, let us use y is equal to c1 y1 plus c2 y2 plus c and yn so on in given linear differential equation number 1. If it satisfies it, that it makes 0 is equal to 0, it satisfies, then we say this is also the solution. You see how when we use it, it gives you d of nth derivative of this dn of dxn. This is your y, you will write it c1 y1 plus c2 y2 plus c and yn, then plus p1, I am using it in first equation, it is dn minus 1 by dxn minus 1, y you will replace by this c1 y1 c2 y2 plus c and yn, then plus p2 dn minus 2, n minus 2 are derivative of dxn minus 2, again c1 y1 plus c2 y2 plus c and yn, then plus so on. Last but one is pn minus 1 d of dx of c1 y1 c2 y2 plus cn yn. I am replacing y by this, and then it is p of n, what is y, c1 y1 plus c2 y2 so on to cn yn is equal to 0. I am using this value of y, which I have to prove is also the solution in the given equation. Now you see, we have the derivative of sum of the function is sum of their derivatives. You know, when we differentiate the sum of functions, differentiation of f1 plus f2 plus f3 with respect to x is d of f1 with respect to x plus d of f2 with respect to x. So we can distribute actually it is an operator, differential coefficient. So when you operate with this, it means differentiation of this plus differentiation of this and a derivative of this. But here c1 is constant. c1 is constant. You can in multiplication you take this constant out. You can write when you distribute this, this will be your c1 dn y1 by dxn plus c2 dn y2 by dxn plus so on to cn d and yn by dxn. This is the first term we have distributed. Similarly, here you can write p1, this is c1 dn minus 1 y1 dxn minus 1. Just I will give the light, which is going dim. Okay. This is plus c2 dn minus 1 y2 by dx n minus 1. Last is here plus cn d n minus 1 yn by dx n minus 1. Well, similarly you have this term will be then plus p2. How you proceed? It is c1 d n minus 2 y1 dxn minus 2 plus c2 d n minus 2 y2 dxn minus 2 a derivative. Last is here cn it is d n minus 2 yn by dx n minus 2. Close this. Now come here, this will be p n minus 1. This is c1 dy1 by dx plus c2 dy2 by dx plus so on to cn dyn by dx. Last it is plus p c1 y1 plus pn c1 y1 pn c2 y2 plus pn cn yn dash dash. Here you will take it dash 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 pn cn yn is equal to 0. Now you will combine the terms. You see where you have c1. Yes, I will take this term, this c1 term, this is here c1 term, connect this. This is c1 term, this is c1. Then I will connect c2 terms. This is c2 term, this is your c2 term here, this is your here c2, it is c2, this is here c2, this is here c2. I will combine accordingly. I will make the groups, that is taking c1 common. When you take c1 common, what you get? This is d n minus 1 y1 by dxn, then plus there plus here p1, c1 is out, p1 d, this is p d n minus 1 y1 dxn minus 1, then plus so on to last will be here. This is pn minus 1 dy1 by dx plus pn y1. Last one, this is this. Similarly you can have by grouping, you group the terms. I will write, you can write it now directly, you will come to know what we get. Now you connect the c2, you will get here d, this is dn here, I'm sorry, this is dn d raised power n, sorry, c2 it is dn y2 dxn plus p1 dn minus 1 y2 dxn minus 1 so on p of n minus 1 dy2 by dx, then plus c2 is out, it is pn y2. Then finally you get here taking Cn out, it will be dn yn dxn, then plus P1 dn minus 1 yn dxn minus 1, so on to Pn yn is equal to 0. From above step, I have taken C1 here common, you have got this thing. Taking C2 common, you have got this thing. That means here we get the again given differential equation with y replaced by what? Y1. Here we get again the given differential equation with y replaced by y2. Again the given differential equation with y replaced by yn. But by second we know this is 0 because y1 is a solution. Y1 is a solution. Using second and third, now using second, third, so on to 4 equations, where you have this 0, you have C1, this is 0, this is C2, this is 0, this is Cn, this value is 0 there, it is 0, so you get 0 is equal to 0. So what we have verified? You have verified, yes, so this verifies that y is equal to C1 y1 plus C2 y2 plus Cn yn is also solution of given differential equation of first. It is called complete. This will be called complete solution of equation first with constant coefficients. So very important. Some of you might have done these questions, second order differential equations, where you get sometimes the solution of the auxiliary equation, say m is equal to m1 m2 or d is equal to m1 m2. Then you write the solution as e raised power m1 is one solution, e raised power m2x. Then you write general or complete solution is y is equal to c1 e raised power m1x plus c2 e raised power m2x, because that is the second order differential equation with constant coefficients. It will involve 2 constants. When you have third order linear differential equation, it will involve 3 constants. When you have nth order differential equation with constant coefficients, and note that here right side is 0. We will deal with when right side is not 0, when right side is x. There you will have the 2 parts of the solution. One will be called the complete complementary function, and second will be called particular integral. That we will discuss within the next lectures. But here we have a very important observation that I want to share with you, and you will also remember. This is the observation of this result. This is observation, what you observed in this theorem. The observation is this: the solution of nth order linear differential equation, you have seen, आपने देखा, what was the solution? Y is equal to C1 y1 plus C2 y2 plus so on to Cn yn, where y1 y2 so on to yn are independent solutions of given equation. And we have seen that when we introduce the constants, different constants, linearly independent constants C1 C2, this also becomes solution. So this implies actually the number of, it is very important, the number of arbitrarily constants, the number of arbitrarily constants involved in the complete solution, the number of already constants that are involved in the number, how many they are, the number of arbitrarily constants involved in the complete solution depends upon what? Depends upon order of the linear differential equation. It is very important. If the linear you have seen in the ordinary differential equation is previous way, when we used to solve dy by dx plus py is equal to 0, or we solved the ordinary differential equation of first order and first degree by different methods, somewhere in a variable separable method, sometimes in the homogeneous method, sometimes in the exact method. You have seen that was a order first and it involved only one constant. But when order increases, order is 2 constants. When order is 3 constants. Order is n constants are involved in the differential. So when you get the independent solutions, one solution is e raised power alpha 1x, second is e raised power alpha 2x, alpha 3x. When we write complete solution, you write there number of constants c1, c2 and connect these by this is known as linear combination method. Linear combination method, we write the solution in a linear combination form. Okay, this is very important. The students, I have already told you in the beginning, the students who are pursuing the this undergraduate courses in this what is called this 5-year integrated course in mathematics, especially in our Kashmir, the JKI, this Institute of JKIMS, Institute of Mathematical Sciences, they should probe the proof. They should probe the proof, how we prove it, how we prove the theorems, and then applications. But the students who are pursuing the engineering courses, it is also very beneficial for them, but they can just read the proofs, but from examination point of view, you have to stress on more and more application part. But without the this main thing that is involved here, what comes how. So it is very important that we have given you the description of this, where the constants comes, how we connected them, then you are in a position to solve the differential equations. I hope you have understood this lecture, and you will wait for the next lecture. Till then you revise this. Thank you very much. I welcome you to next lecture that will be coming shortly. Thank you very much.